Hello and welcome to the course. In this lecture, we will model the rollout phase, or the ground roll phase, but the version of the landing in MATLAB. Here, as you can see, this is our algorithm, which is so simple compared to the other phases, and which is similar with the ground roll phase, the actual ground roll phase. Here, we have no control. We have only a while loop, which is the velocity is greater than 0.5 meters per second, and the rest is the same. Perform the order integration, pack environment, pack controls, but we don't have the controls here, but recall that landing gears and the speed brake are the controls, so they are packed, but they are not controlled anyways. And we pack states, output flight dynamics as well, and for the next step, prepare for the next step, and it's ended. This is it. And let's go to the MATLAB then. All right, here I'm in the MATLAB. So you know what I'm gonna do. I will scroll up and find the ground roll phase, and which is it's up, and it is here. So let's copy this and scroll down, and let's paste it to here. Okay, this is now, let's call that as rollout. And this is phase now 11, and this is rollout. Okay. Let's continue to our development. Here, I'm going to define a braking coefficient, because remember that our friction coefficient was 0.04 for the ground roll phase, where no brakings are active. But here, I will brake. The aircraft will brake, and therefore I need to define a new friction coefficient for that, and I will define that as mu braking. This will be equal to 0.5. Okay, let's clamp the ZE to 0 for robustness, but we won't need that because we will clamp them to 0 here. Anyways, let's adjust our while loop here. Okay, I'm looking for simlog states, and my condition is while simlog states is greater than 0.5 meters per second. And this is it for the while loop. So let's look at our integration here. I'm on the ground, and after this point, I know that I will not ascend, I will not change my altitude, and therefore I can clamp some states here to 0, like ZT. I don't need to calculate this again because I know that this will be 0. Like I said, the W, I will not have any vertical velocity. Theta and Q as well. This is an approach. This is a nice assumption, especially for the flight dynamics, flight performance analysis. We could have done the same thing for the ground roll phase, but I wanted to show you the derivation of the equations of motion. Here, this is another strategy that we can apply here. This also prevents the while loop to calculate those differential equations again and again and again. It simply assigns to 0 and passes them. This increases the speed of the simulation, but I don't know how this affects the whole simulation when we consider the whole mission profile. But with this way, this is also acceptable, and we can clamp those states to 0 conveniently. So let's scroll down. Here, we also need to clamp our velocities to the ground, our ground constraint. Let's go up for that. Let's copy this. And let's paste them to here. And they will be 0 eventually, so I can also do this. Right, we don't need that. Let's delete those. Okay. Here, everything's okay for the environment, but I need to redefine my environment mu, and I'm going to equate that to my new defined friction coefficient here, like this. Let's look at our controls. My controls elevator deflection is not controlled, but I'm going to assign it to -15. Why? Because I want the negative lifting force, the lifting force that points the ground, to further increase the normal force that further increases the friction force. Therefore, I'm doing this. I'm deflecting my elevators with its maximum value but negative way. This in real also increases drag force, and this is also a nice thing when you want to slow down the airplane. But for simplicity, remember that we haven't modeled the drag of the elevator or the whole horizontal tail deflection. Therefore, we can't have that contribution here, the drag contribution, but we can have the lift contribution here as a positive effect to our rollout phase. My control throttle setting is of course equal to 0. My controls here are deployed, and finally I can call my controls speed brake, and this will be 1.0 there deployed. The rest is the same, so I can run this code then. Let's go. Alright, here are plots. So let's check first the mission trajectory here to see our rollout phase. That happened nice. So I'm gonna zoom in here, and I can already see that it's a nice flat line here. So let's first check the angle of attack then. I expect this to become 0, and here I can clearly see that it is 0. As well as the pitch angle, this is also equal to 0. Let's also zoom in for that. I am far away from that. Let's go here, and as you can see, it is 0, and therefore my flight path angle is also 0. So let's also zoom in, and as you can see, it is 0. My flight path angle elevator deflection, it is maximum, and it is minus 15. Let's look at our forces. Here, let me zoom in, if I can move it like this. First, the lifting force is equal to 0 here. As well as the drag force is becoming 0 because the velocity is becoming 0. That's why the drag force becoming 0. And the reason of the lifting force becoming 0 is the angle of attack. The weight is the same, the thrust is 0, and as you can see, my normal force is changing. Here we have maximum value, and it becomes slightly lesser value. The reason is I'm deflecting my elevator with its maximum value, negative side of course, which creates a downward lifting force that enhances my normal force. And as you can see, as I further slow down, as I decrease my velocity, my effectiveness of the elevator decreases, and as you can see, that contribution slowly becomes negligible, or let's say 0. And here the effect of the normal force here. These are the forces. Aerodynamic moment is 0. It's not 0 actually. It is existed because we are deflecting our elevator, but we clamped it to 0, so there is no problem. We don't need to check these 3 plots. Let's look at our longitudinal acceleration, which we'll see a negative but a bit faster value, I believe. Let's zoom in. As you can see, it has a similar behavior, just like in the rotation part. It is negative because I'm slowing down aggressively, but my velocity is not 0, therefore my acceleration is not 0 still. But when everything's become 0, this will be 0, so there is no problem with this longitudinal acceleration. By the way, my velocity is not totally 0. You know that it's 0.5, and this is okay for us to, we can totally say that, okay, the airplane is stopping. Let's look at our vertical airspeed, acceleration. I expect this to become 0, and it is 0. Let's look at our ground speed. As you can see, it decreases to 0.5, like this. We have seen this trend already from the rotation part, and as you can see, it becomes aggressive because our brakes are active right now. This was the speed brakes, and these are the speed brakes plus my gear brakes. Climb rate, again, I expect this to be 0. Let's look at that. I went too much. Yeah, we're right. Let's look at our true airspeed. Again, this has the same trend with the ground speed. Let's look at our Mach number. Again, they are similar right now. And as you can see, I'm also slowly become 0. Let's finally check again our mission trajectory here. And this is our landing profile. Like this. This is it for this lecture, but before ending this video, let's finally run our visualization code, but this is for descent. So let's go. As you can see, we are in the descent phase. Our Mach number slowly decreases. My pitch angle is negative. My altitude keeps decreasing. My throttle is 0. Preheat is off, therefore. My specific excess power is therefore negative because I'm losing my altitude. You can see the distance flown, the fuel flow is therefore 0, and instantaneous range and instantaneous endurance, they are now useless because I burn no fuel. Here in the approach phase, as you can see, my pitch angle became 5, my Mach number became more slower, and you can see my controller is active, slowly makes my throttle 0 to 0.5, and we did this in the approach phase. Therefore, my values are changing here, and here the phase flare, my afterburners are on, as you can see, and I touch the ground, and this is the rotation phase, and I slowly stop right now. Okay, this was it for the simulation and mission complete. Anyways, this is it for this lecture, the rollout phase. The next video will be our closing video. We will discuss what we have achieved and what could have been better. So until then, I thank you too much for your attending and watching, and I'll catch you later.